section here, 11.3, we're going to do this over 2 lessons. We're going to be looking at the binomial theorem. So this is a way of expanding a binomial. So we already know from, 10C how to expand a binomial that's squared. We're going to look now, how do I expand it when it's cubed, exponent 4, exponent 5, etc. There's some patterns that we can kind of go through. And then once we have the patterns under our belt, we're going to look at how do we determine a specific sum. So let's start with this one here, just nice and simple. The binomial x plus y, we're going to expand that to an exponent of 0, 1, 2, and 3. So in the first one, anything to a 0 exponent is always just 1. And then x plus y to the exponent of 1 is just x plus y. X plus y squared, that's just x plus y times x plus y. So distributive property, that would be x squared plus xy plus yx plus y squared. So middle term is the same, xy and yx, there's 2 of them. So this would just be x squared plus 2xy plus y squared. Okay, and then we're going to look at cubing it. So cubing it just means I'm multiplying it by itself 3 times. Okay, so I'll have x plus y times x plus y times x plus y. So I already know what this is because I just did that previously. That's just x squared plus 2xy plus y squared, and I'll multiply that by x plus y. So distributive property, let's distribute x inside. So that's going to be x cubed plus 2x squared y plus xy squared, plus I'll distribute the y inside. So that's x squared y plus 2xy squared plus y cubed. Okay, and then I'm just going to group my like terms. So I'll have x cubed plus I have 3x squared y's, and I have 3xy squared, and I have a y cubed. Okay, so we're going to look at this, and we're going to look at some patterns involved with this. Just a little bit of a tip here, when we're writing any terms of an expression, I always want you guys to write them in alphabetical order. So notice I wrote it as x squared y, not yx squared. And then when you're writing them in alphabetical order, you're also writing them in descending order of your first variable in alphabetical order. So all that means is that if we have a variable x and y, x comes first in the alphabet. So I do it in descending powers of x. So you see I do 3 and then 2 and then 1 and then this is really like none. That's all that that means, okay? So just a good common convention way of writing variables that we want to get in a good habit from the very first step. So let's look at those patterns that I just did in the expanding. And I'm just going to look at the patterns of the variables. I'm not going to worry about the coefficients quite yet. So when I had it to the exponent of 0, it's just equal to 1 because any base to the 0 is equal to 1. Let's look at what's happening with my x exponent. I'm just looking at the variables x and y. So when I have x plus y to the 1, I start with x. Notice here I have an x to the 1. And then really, if we look over here, I'm just filling in the x's and the y's. So see how I just had x and y? That really means I don't have a y here. I can do y to the 0. And I don't really have an x here, which is x to the 0, just so we can start to see the patterns. So when I have x plus y to the 1, it was just x plus y. So it's an x, no y, no x, and then a y. So just looking at the x, see how I start with 1 and then I go down to 0. When I had x plus y squared, just filling it in again, anything that was missing, I put it in as a 0. So I have x to the exponent of 2, 1, and none. And then I had x plus y cubed. So again, notice I start with x and I do 3, 2, 1, and none. So really I'm starting with whatever numbers on the outside, the exponent, and I'm decreasing it until I get down to 0. So x starts at the exponent and decreases by 1 until you reach 0. So I'm going to use this pattern here to do x plus y to the exponent of 4. So again, we're just focused on the variables right now. So I know it's going to start at 4, and then it's going to go down 3, 2, 1, and none. So that's the pattern for x's. Let's look at the pattern for y. So if I look at y, for my second variable, I have 0 and then 1. So I build up to this exponent. Here, look at this one here for y. I start at 0, 1. I build up to the exponent of 2. I end with the 2. Okay, for this one here, I start at 0. I go 1, 2, and 3. So I'm building up to that exponent of 3. So for y, it looks like I start at 0. I increase by 1 until I reach the value of the exponent. So starting at 0, I'm going to go up by 1. And I'm going to go all the way up until I reach my exponent, which is the 4. Okay, and so I'll just put some adding in between there. So right now we're just focused on the variables. Okay, now let's look at the number of terms that we see. So let me do that in a different color. When I had, and I'm just going to erase all this here so I can see what I'm writing out here. Okay, so when I had it to the exponent of 1, I had 1 term. When I raised it to the exponent of 1, I had 1, 2 terms. The terms are what is separated, the polynomial separated by adding and subtracting. When I raised it to the exponent of 2, I had 1, 2, 3 terms. I think I start to see a pattern. When I raise it to the exponent of 3, I have 1, 2, 3, 4 terms. 4 terms altogether. So let's see if that works over here. If that pattern works, it kind of looks like it's always one more. So if I grab it to the exponent of 4, I should expect to see 5 terms. 1, 2, 3, 4, 5. And yes, it does work. So what pattern do I see with the number of terms? I can say that the number of terms is equal to the exponent, whatever the exponent is on the outside of the binomial, plus 1. Okay, so we have some patterns going on there with the variables and with the number of terms. Let's now look at patterns that I see with the coefficients. Okay, so now I'm going to be looking at the numbers and then I'm going to put it together. Okay, so looking at the coefficients. So I have a 1 and then a 1 and a 1, a 1 and a 1, a 1 and a 1. So it kind of looks like I'm starting with a 1 and I'm ending with a 1. So when I expand x plus y to the exponent of 4, I know there's going to be 5 terms. We just discovered that. Exponent plus 1. So I'm going to have 1, 2, 3, 4, 5 terms. And based on this pattern, I know I'm going to start and end with a 1. Now, let's look at what's going on here for the other ones. So where is this 2 coming from? If you look above, what did I do with my coefficients to get a 2? Well, I can see here that 1 and 1, if I add those together, I get 2. Okay, let's look at the next row. 3. Look above, where did the 3 come from? 1 and 2 is 3. Look at this 3. 2 and 1 is 3. So it looks like I'm adding the ones above it. So starting with a 1 and ending with a 1. Now let's look here. So here I'm going to have 1 and 3 is 4. 3 and 1 is 6. 3 and 1 is 4, and I end with my 1. So let's put this all together. So putting it all together, what I did in the last step, I had all of the patterns with the variables. I'm going to put that with the coefficients. So I'm going to have 1 x to the 0, no, sorry, x to the 4, y to the 0, plus 4 x cubed y, plus 6 x squared y squared, plus 4 x y cubed, plus 1 x to the 0, y to the 4. Now let's tidy that up just a little bit more. So instead of having a 1, I can just write it as x exponent 4. I don't have the y, so I can just leave it. Plus 4 x cubed y, plus 6 x squared y squared, plus 4 xy cubed, plus, I don't really need the 1, x to the 0, I don't need to record that, y exponent 4. So that would be my final answer. Okay, so we definitely see some patterns going on with the variables and with the coefficients. Now let's go back to that pattern with the coefficients. It actually is based on Pascal's triangle. So Pascal's triangle is a recursive pattern. It depends on the terms before it to generate it. So I always start with a 1, end with a 1, and then I just add the terms above. So this is the one that we just did. If you go back over here, see the 1, 4, 6, 4, 1? That was this row right here. Okay, so I know I did it right. So you just continue the pattern. So start with 1, end with 1, add the 2 from above. So I have the first 6 rows there. If I wanted to write the 7th row of Pascal's triangle, I start with a 1 and I end with a 1. Now I'm always going to have one more term number, right? So when I had, like, say row 6, I'm going to have 1, 2, 3, 4, 5, 6, 7. If I have row 7, I should expect to see 8 terms. So adding from above, the 1 and the 6 add to 7. The 6 and the 15 add to 21. The 15 and the 20, 35. 20 and 15, 35. 15 and 6, 21. 6 and 1, 7. That would be my 7th row of Pascal's triangle. So again, some patterns. Notice I start and end with 1. And then notice these are mirror images of one another. Okay, that's always going to happen with every single row. Okay, so we're going to put everything together. We're going to put the patterns of the coefficients, the patterns of the variable, put it all together to expand something. So let's look at now x plus y to the exponent of 6. So I'm looking at the 6th row of Pascal's triangle. So the 6th row of Pascal's triangle, if I go back here, this is row number 6. Okay, it has 7 terms. So I'm just going to write those all out: 1, 6, 15, 20, 15, 6, and 1. So there I have it all recorded there. Okay, then let's talk about our patterns of x, x being the first one here. Remember, the pattern was we start at 6 and we decrease by 1 until I reach 0, which I do here. Okay, the patterns for my second term, y, I start at 0 and I increase by 1 until I reach my exponent, which was 6. Okay, so I always like to write it out vertically to help me expand it. So let's write our final answer down here horizontally. So I have here 1 x exponent 6 y exponent 0. That's just x exponent 6 plus 6 x squared y plus the next row here 15 x exponent 4y squared, and so on. So I have 20 x cubed y cubed, 15 x squared y exponent 4, 6x y exponent 5, and add on y exponent 6 at the end. So that would be my total expansion. Now this is great with the patterns for x and for y, but I need to come up with a better way of doing the coefficients, because I don't always want to be writing out Pascal's triangle to figure out what each row is. Like, let's say I asked you to expand something to the exponent of 11. That means that we're going to have to write out 11 rows of Pascal's triangle to be able to do this. So there's got to be a better way. And that better way comes with combinations. Okay? So let's look at this. If I have x plus y to the 0, notice I start with 0c0, which is just 1. If I have x plus y to the 1, I have 1c0, and then I go 1c1. So I'm building, starting at 0 and building up. If I have it to the exponent of 2, so notice these are all 2c, and I start 0, 1, 2, building my way up. If I have something that's cubed, so starting with the 3's, they're all going to be 3c's, and I start 0, 1, 2, stop at 3. Okay? So based on this pattern here, if I want to write the 7th row of Pascal's triangle, I know it's going to be all 7's. So 7c, starting at 0, 7c1, 7c2, 7c3, 7c4, 7c5, 7c6, and I stop when I have a match. So I start at 7. They all have 7's. I start from 0 all the way up, and I stop when the numbers match. So now that we've done this, we don't need Pascal's triangle to write out all the terms from before. So for example, if I have x plus y to the exponent of 5, notice these are all 5c's. So 5c, 0, 1, 2, 3, 4, and 5. We can put that together with our pattern for x and for y. So all I have to do is come up with what all of those are on Pascal's triangle. 5c, remember that trick I showed you guys from the last section, 11.2. So this is 5c1, which I can see is 1. 5c1 is 5. 5c2 is 10. This one's also a 10, and then a 5 and a 1. Again, mirror images of one another. So x being my first term, I start at my exponent of 5 and I decrease by 1 until I have an exponent of 0. For y, I start at 0 and I increase by 1 until I reach my exponent of 5. Okay, so I can put all of those together with the expansion. So 1 times x exponent 5, y exponent 0 is just x exponent 5. And then I have 5x exponent 4y. And I have 10x cubed y squared, 10x squared y cubed, 5x y exponent 4, and just a y exponent 5. So that would be how it expands. Okay, so let's summarize the patterns that we've come up with so far, and we're going to build on these patterns. So the first term, which was x, was raised to exponents of n being the exponent on the outside, decreasing until 0. The second term, y, started at 0 and increased until it reached n, which again was the exponent. There was always one more than the exponent number of terms, and we found the coefficients that went with that using Pascal's triangle and combinations. Okay, now here's something I didn't mention yet. The sum of the exponents of the first and the second term will always equal 1. Let me go back here and show you what I mean. 5 and 0 is my exponent of 5. 4 and 1 is 5. 3 and 2 is 5. 2 and 3 is 5. 1 and 4 is 5. 0 and 1 is 5. Sorry, 0 and 5 is 5. So because 1 is decreasing, 1 is increasing, they're always going to add to that exponent. Okay, now not every pattern is just going to be x plus y, but we're going to use the idea of first term x, second term y to expand this. So here is a difference. I'm going to still use the same ideas, but my first term isn't x, my second term isn't y. In this case here, my first term is a 2, and my second term, paying attention to signs, is a -3. So let's start with our coefficients. Since I'm raising this to the exponent of 4, all of my combination, my coefficients, are going to be 4c's. So 4c starting at 0, building its way up to 4. So I can put those on my calculator to figure out what the exponents are. Oh, and that didn't show up. That's okay, I have them. Okay, so 4c0 is 1, 4c1 is 4, 4c2 is 6, 4c3 is 4, and 4c4 is 1. Okay, so normally that would be done on the calculator. I don't know why that wasn't showing up, but that's how I got all those numbers. Okay, my first term is 2. So I'm starting 2 at my exponent 4, and I'm going down by 1 each time. My second term is -3x. Again, really important that you pay attention to the signs. So I'm going to start my second term at an exponent of 0 and go up to 4. So I can always check to see if I've done this right just by looking at my exponents. So see here how I have 4 and 0 is 4. 3 and 1 is 4. 2 and 2 is 4. 1 and 3, and 0 and 4, always 4. Okay? So let's multiply these together. So for my coefficient, I'm going to have 1, 4, 6, 4, and 1. Okay? Then I'm going to have 2 exponent 4, which is 16. 2 cubed is 8. 2 squared is 4. 2 to the 1, and 2 to the 0. And then in the last one, anything to the 0 is just 1. So -3x to the 1 is just -3x. -3 squared is 9, and x squared. Negative 3 to the exponent of 3 is negative 27x cubed. And negative 3 to the exponent of 4 is 81, and then x exponent 4. So now to expand this, all I have to do is just multiply my numbers together. So 1 times 16 times 1, that's just 16. And then minus, because this is a negative, so I'm going to multiply 4 and 8 and 3 together to get 96x. Okay, now I have a positive. 4 times 4 times 9, 216x squared. 4 times 2 times, well, negative means subtract 27 is 216x squared. And then 1 times 81 is just 81x exponent 4, and that's positive. Okay, so that's how it looks. That's a good answer. What a better answer is to go in descending powers of x. So a better way of writing that would be starting with the x exponent 4 and decreasing from there. Okay. Now, because I only have one variable, I could check this on the calculator. If I want to know, did I do this right, I can put left side into y1, right side into y2, and I can just check, are they equal? Remember, the check always happening in the table. So that's exactly what I did. Left side in y1, right side in y2, and you can see for all values they are equal, which means I did my expansion correctly. Okay, so we're going to do one more example where the variable is the same for both the terms. And I just wanted to do a fairly quick review of our laws of exponents. These are the ones that we use the most. Negative exponents, power of power, quotient law, and zero exponent we've already talked about. We're going to use that because in this next example of a binomial expansion, we have only one variable, which means we'll have to use our laws of exponents to simplify. So if we look at this one here, I've got a squared minus 1 over a cubed. So my first term is a squared. My second term, instead of saying negative 1 over a, I said it's negative a to the negative 1. So I used my negative exponent rule there. Okay, so looking at the exponent of 3, all of my coefficients are going to be 3c's. So 3c0, 3c1, 3c2, 3c3. Ooh, that one worked out this time. Okay, so this is just 1, 3, 3, and 1. Okay, my first term is a squared. So a squared is going to be to the exponent of 3 all the way down to 0. Okay, so to the exponent of 3 all the way down to 0. My second term, I'm writing it as negative a to the negative 1. That's going to start at 0 and increase until it gets to 3. Okay, so let's write out what we have so far. So for my coefficient, I have 1, 3, 3, and 1. Okay, so for this is power of power law. A squared cubed is a exponent 6. A squared squared is, you multiply them together, is 4, and then a squared, and then a to the 0. Okay, now let's look at our second term. So anything to the 0 is 1. Okay, and then this is going to be negative a to the negative 1. Let me write that again. So negative a to the negative 1, 1 times negative 1. A negative squared is a positive, and it's going to be negative 1 times 2, negative 2. And then a negative cubed is negative, and then negative 1 times 3 is negative 3. Okay, so we're going to multiply those together and write the result. So 1 times 1 is 1, so I have a exponent 6. Take away, because that's a negative, 3. And then this here is product law. So 4 take away 1 is 3, a cubed. And then I have plus 3. And then a to the 2 take away 2 is 0. A to the 0 is just 1. So I can leave it as just 3. There is no a value. Okay, plus, no, minus, because it's a negative. And then I have 1 times negative 1 is negative 1. And then a to the 0 times a to the negative 3. 0 take away 3 is a to the negative 3. Okay, so that's a good start, but I want you guys to keep it positive. Your final answer cannot have negative exponents. So a better answer is going to be a exponent 6 minus 3a cubed plus 3 minus 1 over a cubed. So just write it like that. Okay, so to summarize this lesson here, our first term in the binomial expansion is raised to the exponent of n and decreasing exponents until 0. Our second term in the binomial expansion is raised to the 0 and increases to an exponent of n. The coefficients again can be found using Pascal's triangle or combinations. Remember, you start your combination with whatever your exponent is. So if I have something cubed, all of my combinations will be 3. 3c, 0, 1, 2, all the way up to 3. So you start at 0 and go all the way up until your n value. And remember, there is always one more term than the variable, than the exponent. So if I raise something to the 4, 4 plus 1, 5 terms. If I raise something to the 6, 6 plus 1, 7 terms, etc. Okay, so hope this is a good introduction to binomial expansion so you can apply it properly and not expand like this student did.